Alright students, today we are discussing 2024 current electricity essay questions. Actually my students, they know that I am not a big fan for current electricity essay questions. So what I am saying you students, it takes time for the calculations and calculations may be a bit hard. So there are 10 powers of 10 and all that, and the calculation may go wrong sometimes compared with electronics question, but it is your choice, right? So before selecting this question, actually you have in the real exam, actually what you have to do is at least you have to cover 10 to 15 essay questions and then you pick this question. So once you have the confidence to pick the question, it's always better, right? No worries with that. Actually if you pick current electricity questions, students, you are not doing electronics question, where this question, if you really know your theories, when it comes to calculations, it's really easy. So accuracy is very high. It's your choice selecting the question. Right, let's get into the 2024 current electricity question. Hello students, we are at the beginning of 2024 current electricity question. Let's get into the question now. Right, a thin heating element made of a conductive material of resistivity rho, let's draw the value. Rho has the shape of a rectangular strip with a length L. So this is the length, and with W and thickness T, of course, you can see as shown in the figure 1. Right. Write down an expression for the resistance R of the heating element in terms of rho, L, W and T. Basic equation, students. Resistance of a wire, you should know this equation, R equals rho L over A. Right, so rho, of course, that's given, and resistance of the wire L, and cross sectional area. So this is where the current flows, students. Through this point current goes in, so we need to get this area, that's length W and T. So W into T, this is the expression they are looking for, right? And we are given certain values in the next part. If L equals this value and W equals 20 millimeters and T equals 5 micrometers and rho is given, calculate the resistance of the heating elements. Easy. You need to apply the values. Rho equals 8 into 10 to the power minus 5 L, that's 100 millimeters. So I have to convert into meters. Remember students, 10 to the power minus 3, and W, of course, 20 into 10 to the power minus 3, and 5 micrometers, 5 into 10 to the power minus 6. If you do not remember these things, milli, micro, nano, pico, 10 to the power minus 3, 10 to the power minus 6, 10 to the power minus 9 and 10 to the power minus 12. Right. Let's simplify. Right. I'm going to simplify in this method. 20 into 5, that's 100. Okay, that's 100, of course you can see 100 here, 10 squared, 100, and 10 to the power minus 3 and 10 to the power minus 6, right, of course you can see. And then 100 into 10 to the power minus 5 will be 10 to the power minus 3, 10 to the power minus 6 into 8, right. 10 to the power minus 6, 10 to the power minus 6 cancel off, and 10 squared, 10 to the minus 3, only 10 to the power minus 1 will be remaining there, so that goes up 80. That's the answer. What's 80? 80 ohms. That's the resistance of this heating element. Alright students, now we are in the second part of the question, part B. Now all those, let's read the question first, right? As shown in the figure 2, this is figure 2, right? As shown in the figure 2, a variable heating pad is designed for localized heat therapy. Using the above thin heating elements, the heating elements are arranged as shown in the figure. The heating elements are arranged in the figure along with 40 ohm standard resistor. You can see it here. The pad is connected to 24 DC source with negligible interresistance. Thin heating elements are represented by rectangles here, and the heating pad should produce at least 7 watt to deliver the required heat, right? So here first one, they are asking from us to calculate the resistance of branch AF. I haven't drawn it. Here A, here B, and here it's C. Right, calculate the resistance of branch AF. So to calculate the branch AF, we need the, so they're asking calculate the branch F resistance. So we need to know the resistance over here. That of course we have found earlier. It was 80 ohms. So here it's 80 ohms. Here it's 80 ohms. Here it's 80 ohms. Here it's 80 ohms. Here it's 80 ohms, and here they have given it's 40 ohms. Here it's 80 ohms, and here it's 80 ohms. Here it's 80 ohms, right? Between A and F, students, you can easily see its current electricity. These three resistors are parallel to each other, so are series, right? So you can directly add them, 80 plus 80 plus 80. So 80 into 3, of course. So it's 80 plus 80 plus 80, that's 240 ohms. That's the answer, right? Then students, BF, again these resistors are series. 80 plus 80, 160, that plus 40. So 80 plus 80 plus 40, 160 plus 200 ohms. Right. Calculate the current to branch BE. Next one. Right. So now they have given us the current the potential supply is 24, and this 24 volt is given between AF, BE and CD. Each of these combinations are parallel to each other. You can see it. Right. Let's apply simply V equals IR. Then you can find the current. V equals IR across AF across BE. So potential difference is 24. That divided by the current we have found earlier is 200. So 12, yes, 0.12 amperes. That's the current through BE. Right. Calculate the current through branch B. Calculate the power dissipation in the branch BE and the entire circuit. Does the heating pad produce the required power? Right. Now they are asking us to find the power. Right. So to find the power, of course, students, you should remember the power equations. So what are the power equations? First one that should come into your mind from all levels. P equals VI. All levels of all A levels, right? P equals VI. And what's the other equation? V squared over R, and the last one I squared into R. So we have to use one of these three equations. So here the easiest one to use is V squared over R here. So we are given the voltage and resistance is available. So let's try that over here. Finding the power, right? So between heating elements is right, okay? So BE power, let's find BE power first. So I'm going to apply V squared over R equation. So the potential difference across BE, that's 24 squared. So I'm going to write it as 24 into 24, that divided by BE 200, right? So 24, 12, and it's 100. Let's multiply 24 into 12, 12 into 4, 48, 4 balance, 12 into 2, 24, so 28, double dot, so 2.88 watt, that's the power dissipation across BE. Right, now let's find power dissipation across AF. Very same method, 24 into 24, right, and the resistance is 240. It's kind of easy to simplify. 24 1, 24 10, so it's 2.4, yes, 2.4. So they're asking us the total power dissipation. So what we have to do is we have to add them. So there are 2.4, 2.4 here, and 2.88. So 2.4, 2.4, 2.88, 8, 448, 16, right? Yeah, 448, 16, 1, 3, 2, 7, 7.68 watt. That's the total power dissipation in the circuit. Moving into the next part. If the calculate the total power dissipation of the circuit if the thickness of the heating element is halved, right? Here it's tricky. You don't have to do all the calculations, students, here. So what basically they are telling is resistance R equals rho L over A. And earlier we wrote the equation, it's T into W. So they are going to make this T as half. So it's T half. So you can see easily this 2 goes up. So that's 2 rho L over TW. Basically what actually happens is the resistance increases, it gets doubled. So previous it's 80 earlier, now it's 160 over here. So total resistance across AF will be 360. So 3 into 160, it's 480 ohms. I hope you can see it. Again here of course 480 ohms. Here we need to add 160 plus 160, that 320 plus 40, 360 ohms. We have all the values now. Now we need to find the power again. Power dissipation. So across BE, very same method, V squared dou R. V squared, let's try it in this color, 24 into 24 divided by, now we have 360 across BE, right? 24, 6, 360, 60, again another 6, it's 4 here, right? So 6, 10, 6, 4, 4 into 4, 16 divided by 10, it's 1.6 watt. The new power across BE, now it's 1.6, right? Now we are going to go against across AF. Very same method we applied. V squared 24 into 24, that divided by 480, just like the previous method. Actually this is kind of easier to simplify. 24 1 and it's 20, so 2.4 divided by 2, it's 1.2 watt, right? The total power, so there are two, here it's 1.2, here it's 1.2, that's 2.4. 2.4 plus 1.6, 3 and 4 watt. That's the total power once the element, the thickness becomes half, right? Right, moving into the fifth part. If the length L is equal to the width W, right? It's actually, we should draw here, right? If the length is equal to the width W, so it's basically L over here, and show that the resistance is independent of the surface area LW of the heating element shown in the figure 1. Right, this is figure 1. What was the previous equation? R equals rho L over, what was the value? Over TW. So here now they are changing the question. They are telling W becomes L. So TL, so L and L cancel off. You can easily see it's rho divided by T. So you can easily prove that it's independent from L. TW. The TW, LW is not the LW. LW is the surface area. It's independent, right? Sixth part. Calculate the resistance per unit square of the top surface of the above heating element having thickness 5 micrometers. Now we know square, it's independent from the surface, so just simply you have to apply rho and T over here. So it's rho is, what's the value, 8 into 10 to the power minus 5 here, divided by thickness 5 micrometers, 5 into 10 to the power minus 6. So 10 to the power minus 6, 10 to the power minus, cancel, this goes up, so only 110 remaining, right? So 80 divided by 5, that will be 16 ohms. That's the answer for the sixth part, right? So we are moving into the Last part, part C. And part C and D. Right. That is part C. Right. Let's read it. Assume that a heating pad contains resistive elements made of two thin layers deposited on top of each other. Right. So here we have one layer and here we have another. Right. So we've got two. Right. And layer 1 above 1 made of a material with a resistivity that remains constant with temperature. So rho will not change with temperature. It won't change. And the second one made of a material with the same resistivity as layer 1 initially, but resistivity increases as the temperature increases. So rho increases as the temperature increases. The heating pad operates using a constant voltage source. Giving reasons, explain what will happen to the power dissipation of the modified heating pad over time. Right. So simply what students actually happening here is, so basically they are asking about the power. So what's the power equation? V squared over R. So V of course will not change because it's a constant potential supply they are telling it. So resistance here, when actually current goes to material, basically it gets heated because of Joule heat. So what happens here is this resistivity will not change with temperature. So R equals rho L over A. So if rho doesn't change, then R will not change. So here the power will remain constant, the above layer. And when it comes to second layer, the resistivity will increase with temperature. So the power will, basically what happens? V squared over R, when resistance is increased, so power will go down, power will decrease. So altogether for this heating pad, the power dissipation will decrease. That is your conclusion for this question, part C. Moving into part, let's read it. A DC source to supply power to circuit can be constructed using suitable step-down transformer. So this part actually from magnetic field. Here a transformer is used to step down an input voltage of 240, right, 240 volt RMS to an adjustable output of 12 volt and 48, 12 volt or 40 in between. The transformer has 800 primary windings. Okay, I'm just writing down the details. At the output stage, the transformer output is converted to DC voltage. So that's converted by using a diode, half wave regulator or full wave regulator. That's electronics. Right. So first question, write down an expression for the ratio of primary. Right. So step down transformer. Right, step down transformer, they are asking us to write down an expression. Ratio of primary voltage Vp and Vs of the transformer in terms of number of windings. So students, this is theory question, basic theory questions. So I hope you know this equation. Vp over Vs is equal to Np over Ns. Easy as that. Second part, if the RMS voltage of the secondary coil can be varied between 12 to 48, okay, calculate the range of number of windings required in the secondary coil. Right, when it comes to 12 volt, let's do it here. For 12 volt, Vp, that's 240, that won't change. And the output voltage, we need 12 volt. And Np, that's of course 800, Ns, that's what they're asking from us. So let's subject Ns value here. So Ns equal 12 into 800, okay, divided by 240. So 12 1, 12 20, 0 0, it divided by it's 20, 40 windings. Right. Moving to the next part, then 48 volt, let's throw it here. Again Vp, that's 240. Vs, of course, that's 48. And Np won't change. And Ns, that's what we need to find. Let's subject Ns. So 800 into 48 divided by 240. 24 2, 24 10, 0 0, 2 into 80, that's 160 windings needed. Right, students? Third part. The DC output voltage is 80% of the RMS output voltage of the transfer secondary coil. The DC output, okay, DC is 80% of this secondary coil. 80% of the RMS value, okay. If the desired fully rectified DC is 24, right? So 80% of secondary is 24. That's what they are saying, right? Calculate the output RMS voltage of the transformer. Easy mathematics question, students. So 80% of Vs. Let's write it over here. 80% of Vs is equal to 24. So Vs into 80 over 100 equals 24. Let's subject Vs. 24 into 100 divided by 80. Cancel off 3. Yes, we get 110 here. So it's 30 volt. That's the answer, right? That's part 3, right? Then the last one, the last part of the question. The transformer supplies to a load that consumes 120. Okay. This is connected to a load like this, load resistor that consumes 120 watt, right? If the power loss due to Joule's heat of the secondary is 10% of the power consumed by the load, so it's here the Joule's heat is 10% of this. So 10% of 120 is the loss, right? Calculate the RMS output current of the transformer. Output current I. For ideal transformers, students, I hope you remember this equation. IP Vp equals Is Vs. So this is power, right? So IRMS equals VRMS. So they are asking us IRMS here. So for that, IRMS into VRMS, that should be equal to the power, the power of the secondary coil. So secondary coil is able to give 120 watt outside. And of course, and Joule's heat will be, the loss is 10% of it. So 120 watt, that's the power of this, that's been given by, yes, the secondary coil, and the loss we have to add them. So 120, 10% mean 10 divided by 100, of course you need to know these things. So 120 plus 10% of this is 12, right? Yeah, 0, 0, 0, 0, that's 12. So it's 132 watt. That's the real power of the secondary coil. Now that's IRMS into V. Right. Let's put the values here now. It's 132 here. So they're asking us IRMS. So IRMS equals 132 divided by, what's the value? What's the voltage here? It's 30 volts. So 132 divided by 30 volt, right? So 13.2 divided by 3, here of course 13, 4 and 12, 4.4 amperes. That's the current through the secondary coil, IRMS. Easy as that. Now we have done 2024 current electricity question, right? You might assume that's an easy question, right? There's no valid point, but I was saying at the beginning, yes, students, the thing is that once you hear an explanation, yes, you may feel like it's an easy question, but you yourself have to pace it first hand. Then if you feel like, yes, I can do the question, that's your gut feeling, that you have to try that question. Students, remember that if you are deciding to do current electricity questions or whatever the essay questions, you have to at least try 15 essay questions from past papers. So when you do the questions, you get one question and you do it and you see the marks and you move into the next question. Likewise, you have to check your answers, check your marks. If it's above average, say for a question you get 15 marks, and at least if you can get more than 12, that means you are good, right? You are closer to an A pass, right? So that's how it is. That's how you picked it. So I'm saying check your stats, and if you feel like this question is good, it's always better to go with this question. Remember, students, you are not doing electronics essay question if you are doing this question. So before doing that, actually I'm inviting you to try electronics as well. So it's an easy question but you have to know your theories. Here, of course, you have to know your theories, right? We had power theories, we have current theories, we have magnetic field theories, transformers and all that. So everything come together right here. So just like that. Practice is key, students, as I always say. So practice and try your best for A levels.